Have you ever watched the curved organic light-emitting diode TV? TV needs a luminescence process to emit light and express the image that we see. For the flexible display, a display made using organic compounds that emit light by themselves without the help of a backlight unit when an electric field flows. This is an organic light-emitting diode. The basic principle of emitting light is electroluminescence. Electroluminescence is light emitting by applying electricity to light-emitting materials, especially in organic light-emitting diode, where energy is generated when electrons and holes meet. When an electron in an excited state falls down and meets a hole, the energy of the electron becomes lower and the electron discards its excitation energy as a photon. For releasing energy as photons by electroluminescence, several light-emitting methods called radiative decay processes are used. Here, we will study 4 processes: fluorescence, phosphorescence, thermally activated delayed fluorescence, hyperfluorescence. First, fluorescence is the typical method of electroluminescence. How to make fluorescence? The electron becomes excited by injecting energy into the ground state light-emitting material. Now the electron wants to be stable, so it goes to the ground state in a short time. By this spontaneous emission of radiation occurs within a few nanoseconds after being excited, light with the energy between the S1 and S0 is emitted. This is the spontaneous process because all nature always wants to be stable. Fluorescence is useful because it needs only a few nanoseconds, but it is not efficient due to its low internal quantum efficiency, 25%. Phosphorescence is developed to supplement the drawback of fluorescence, especially low internal quantum efficiency. To increase the internal quantum efficiency, phosphorescence uses the triplet exciton by intersystem crossing. Triplet is spin-forbidden but has slightly lower energy than singlet. Also, triplet has 3 times more available than singlet. Fluorescence uses only singlet, but phosphorescence uses both triplets and singlet. Heavy metals such as IR and point complexes has large orbital and electrons of them are less affected by the central element. So, the excited state of S1 can be transferred to a state called T1. This process is called intersystem crossing, so the triplets make light emission by moving from T1 to S0. Phosphorescence needs a longer period than fluorescence, but it has almost 100% efficiency by using triplets when phosphorescence uses only singlet exciton. Thermally activated delayed fluorescence and hyperfluorescence are the next-generation OLED light-emitting methods currently being developed following fluorescence and phosphorescence. Thermally activated delayed fluorescence and hyperfluorescence both achieved 100% quantum efficiency based on fluorescence. First, let me introduce thermally activated delayed fluorescence. Thermally activated delayed fluorescence is a third-generation organic light-emitting material that achieves 100% quantum efficiency by making the energy difference between energy levels S1 and T1 very small. The thermally activated delayed fluorescence process is as follows. First, heat triplets that is not used in fluorescence and turn it into singlets. Since the energy difference between the energy levels T1 and S1 is very small, the triplet excitons easily shift to S1. This artificial conversion of triplets into singlets is called a reverse intersystem crossing. Since this converted singlets is an excited electron, it spontaneously emits light and returns to a stable state. Thermally activated delayed fluorescence uses triplets that has not been used for this fluorescence, thus achieving 100% internal quantum efficiency. However, thermally activated delayed fluorescence takes more time to generate light than fluorescence due to the addition of the artificial process reverse intersystem crossing in the middle. And OLED using thermally activated delayed fluorescence has the disadvantage of low purity of color. Hyperfluorescence appeared to overcome the disadvantage of low purity of color. Hyperfluorescence add TADF dopant from host and dopant, which are the base materials for OLEDs. This addition of the TADF dopant creates an additional energy level called dopant S1 between the existing S1 and the ground state. Hyperfluorescence, like TADF, moves triplet to energy level S1. And the triplet moves from S1 through dopant S1 to the ground state. Light occurs between dopant S1 and ground state. The color of the light generated in this way has high purity. In this way, hyperfluorescence is conceptually excellent, but it has not yet been commercialized. This is because there is still a lack of development of fluorescence dopant materials in which hyperfluorescence is used. Currently, many scientists all over the world are trying to commercialize hyperfluorescence. In this way, the OLED industry has moved to compensate for existing shortcomings by studying various OLED methods. Now, hyperfluorescence is called the last king of OLED, but someone might find a way to jump hyperfluorescence. Why don't you become the main character in the development of OLED technology? Thank you for watching the video so far.